In this next example here, we have this function log base 3 of x plus log base 3 of 6 equals log base 3 of 42. First things first, I want to state my restriction. My restriction is only on that x there, so x has to be greater than 0 because we have a vertical asymptote going right through 0. Here, what we're going to do is combine these first two on the left together, and the way that we're going to combine these logs together is to say if I'm adding, really that means I'm multiplying. So I'm going to go 3 times, or sorry, x times 6, which is now 6x here on the left. This is equal to log base 3 of 42 on the right. Now that I have common bases, common logs on both sides, and it's a single log on both sides, I can drop my logs. So that log 3 goes away. So I'm left with 6x equals 42. And here I'm going to divide both sides by 6. Divide by 6 to get x by itself. So x is equal to 7. And again, let's double check. Does that fit in our restriction? Sure does, because it's greater than 0. So I could put a box around this answer for our solution. In this next example here, again, I want to start off with my restriction. And my restriction is only on x. So here, this just means we had a vertical asymptote at 0. We're shifting it 1 to the left. So this is now x has to be greater than -1. On this one here, we really haven't done anything really like this. So the way that we solve this is we're just isolating for the variable x. So x has to be, so really it's 2x minus 3 has to be greater than 0. So 2x has to be greater than 3. So then x has to be greater than 3 halves. So there we go. We'll probably have a vertical asymptote here at 3.5 or 3 halves, which is 1.5 on your graphing calculator, or greater than 1 or -1. So out of these two, I'm looking for this one here being the biggest one. It'll encompass this one over here. So let's start off with our combining our logs. So if I see subtraction, that really means it's division. So I'm going to go log base 4 of, and I'm going to set up my division statement, x plus 1 up top in my numerator, 2x minus 3 in my denominator there. And that's all equal to log base 4 of 8. Now that I have common bases on both sides, log 4, I can drop my logs and I can just simply work with what I have left over. So I have x plus 1 up top divided by 2x minus 3 in my denominator in the bottom there is all equal to 8. Multiplying both sides to get rid of this denominator, so I'm going to multiply this side all by 2x minus 3. So if I multiply it on this side, I'm going to multiply it on this side here, 2x minus 3. So I multiply it to both sides. These will cancel out, so I'm left with x plus 1 on the left equals, and I'm going to also distribute here on the right. So that 8 is going to be distributed into that bracket there. So I have 16x minus 24 here on the right. Let's combine our x's. Let's get them all to the same side. So if I have x over here, 16x over here, I'm going to move my x's all to the right. So that means I have 15x's now because I subtracted 1x. And I have 1 on the left here, moving this negative 24 to the right. That means I'm adding 24. So now I have 25 here on the right. Isolating for x, x has to be equal to 25 over 15 because I divided both sides by 15, which is the same thing as a reduced fraction of 5 over 3. And 5 over 3, if you can remember, 5 over 3 is definitely bigger than -1, and it's going to be bigger than 1.5 or 3 halves there. So there we go. This is our solution, 5 over 3. In this next example, I'm going to do the exact same thing as the previous few, but first off, let's start off with our restriction. So I'm going to write it right to the side here. So our restriction on this first one here, x has to be greater than 0 because that's my vertical asymptote at 0 here. Over here, I'm shifting that all to the right by 1, so that means x has to be greater than 1. Out of these two restrictions, again, I'm looking at this one here because it's the larger of the two. So what are we really doing when we have addition? We're really multiplying. So here I'm going to combine my logs. I'm going to go x times x, which is x squared, and x times negative 1, which is negative x. That's equal to log base 3 of 6. Here I have log base 3, log base 3. I can drop my logs. That leaves me with x squared minus x equals positive 6. Moving this 6 to the same side, I have x squared minus x minus 6 equals 0. And now to solve for x here, I can factor. So I'm going to factor this out, and that means things that multiply to negative 6 and add to negative 1. So things that multiply to negative 6 add to negative 1 are negative 3. So I have x minus 3 and x plus 2. And I set that equal to 0. And rewriting each factor, so this here is x equals positive 3. And rewriting this factor, x here is equal to negative 2. And again, double checking our restrictions. X plus 3 fits, it's greater than 1. This here is less than these restrictions, so here x equals 2 is my extraneous extraneous solution. For our next example here, example 3, what we're doing is we're trying to solve a logarithmic equation, but this time we're going to throw in a number as well to kind of throw you off. Okay, we're throwing in some numbers to try to confuse you, but again, the way that we're going to deal with those numbers is we're going to convert those numbers into a logarithmic equation. Before we get going on that, I'm going to start off with my restriction. So I'm going to just do it off to the side here. So my restriction is going to be x squared minus 2x, because that's my only variable there. I know that my x squared minus 2x has to be greater than 0 somehow, because you can't take the log of a negative value. So it has to be greater than or equal, or greater than 0, just not equal to. It has to be greater than 0. To solve for this, I'm going to go to my graphing calculator. So here I have my graphing calculator pulled up. I have the equation typed in, x squared minus 2x, and I'm going to put a 0 in for y2. Basically, I'm looking for this graph and wherever it's greater than 0. Well, here's my 0 line. It's greater than 0 right here, so our graph is greater than 0 when x is less than 0, and it's greater than 0 when x is greater than 2. So my two restrictions will be x has to be less than 0 and x has to be greater than 2. So I have two restrictions right now. So now that I have my restrictions in place, I can then solve for my question here. So again, what should we do with this number? I mentioned earlier that we were going to try to convert this into a logarithmic equation. So I'm going to write the following. Of log base 3 of x squared minus 2x, and that's all the same. We haven't touched anything here on the left. That's going to be equal to, well, the only way to change 1 into a log is if we have log base 3. But log base 3 of what would get you to 1? Well, it would have to be 3. Because remember, this 1 acts as your exponent, so this is 3 exponent 1 is equal to 3. So now that we have log base 3, we can actually drop our logs on both sides. So I'm left with x squared minus 2x equals 3. And from here, I'm going to move this 3 to the left side, so I have x squared minus 2x minus 3 equals 0. And factor to solve this now, I have x minus 3 and x plus 1 as my two factors equal to 0. So this here is now x equals positive 3, and this factor here is x equals negative 1. And out of our two factors, let's double check with our restriction. Well, is x equals 3 greater than 2? It sure is. So I'm going to put a square around it to box it off, indicating that's a solution. X equals negative 1. It's not greater than 2 there, so it doesn't fit. However, it is less than 0, so it does fit our restriction. So there we go, boxing that as well, because it does work for our solution. On this side here, let's start off with our restrictions. So restriction on the first one, x is going to be greater than -1. On the second one, x is going to be greater than +3. And again, because that +3 is the biggest restriction, that's usually what I'm going to be working with. I'm going to combine these two logarithmic equations and change this one into a log base 5. Similar with what we did here. Okay, similar with how we did log base 3 of 3, this is now going to be log base 5 of 5. So I have the following. Again, addition means to multiply, so I have log base 5 of x plus 1 multiplied by x minus 3 there in my logarithmic equation. This is equal to log base 5 of 5. And again, the way that we're going to check that, 5 to the exponent 1 has to equal 5 here. Now that I have log base 5 on both sides and it's a single log on both sides, I can drop my logs. So once I drop my logs, I'm left with x plus 1 multiplied by x minus 3, and that's all equal to 5. Let's distribute our binomials. We get x squared minus 3x plus x minus 3 equals 5. So I just x times -3, 1 times x, and 1 times -3. Combining like terms, I have x squared minus 2x minus 3 here, all on the left, equal to 5 still. Moving this 5 over, I have x squared minus 2x minus 8 this time equals 0. And now to finish this one off, I'm going to factor, and my factors are going to be x minus 4 and x plus 2 equals 0, setting each equal to 0, so I have x equals positive 4, and over here x equals -2. Let's double check our restriction because we did it at the beginning. We have a restriction of x has to be just strictly greater than 3 or greater than -1. Well, 4 is greater than 3 and -1, so 4 fits. -2 is not greater than 3, so there we go. This is an extraneous solution, so you don't want to put a square around it. For our last example here, what we want to do is what we've been doing with the previous questions. So first off, I'm going to state my restriction. So my restriction here on that first one is, and I'm just going to write this one out in full, 7x plus 1 would have to be greater than 0. So 7x has to be greater than -1. So x has to be greater than -1 over 7 as a restriction on this first log equation. On the second log equation, x minus 1 has to be greater than 0, of course, so then x has to be greater than 1. So again, because this one is our largest restriction, we're going to use it for both, basically. Let's start solving this one here. So again, I have a number and I want to convert that number into a log base 9 because everything else was log base 9. So on the left here, I'm not going to do anything. I'm just going to copy that down. Log base 9 of 7x plus 1. And this is equal to this 1/2. The way that I'm going to make it into base 9 is I'm going to go 1/2 multiplied by log base 9 of 9. Log base 9 of 9 is just 1, so I'm going 1/2 times 1 ultimately, which does not change our equation. Plus log base 9 of this x minus 1 left over. Here, I need to move this 1/2 up as an exponent because we don't have any coefficients anywhere. So I have log base 9 of 7x plus 1 is equal to log base 9 of 9 to the 1/2, which I can evaluate, by the way. I can evaluate 9 to the 1/2 plus log base 9 of x minus 1. From here, evaluating this, what's 9 to the exponent 1/2? That's the same thing as saying square root of 9. So this is now log base 9 of 7x plus 1 equals log base 9, and I hope that you got it, of 3. And of course, that 3 is now going to be multiplied by x minus 1. And why am I multiplying? because there's an addition sign there, so it's going to be 3 multiplied by x minus 1 in brackets there. So I just combined these two logs. I have a single log on the left, a single log now on the right. I can drop my logs. So I have 7x plus 1 is equal to, and I'm going to show my distribution right now, 3 times x and 3 times negative 1. So this is now 3 times x and 3 times negative 1, which is just negative 3. Here I'm going to combine all my x's together. So moving this 3x to the left side, I have 4x left over. And this 1 to the right side, that's equal to negative 4. Dividing both sides by x, x is now equal to negative 1. And again, I'm going to check my restriction. X equals negative 1. Is that greater than positive 1? No. So this here is an extraneous solution. And there we go. If you have any questions about today's lesson, please feel free to ask.